Hello, my name is Roshni Purohit, and this is Lab 2, Projectile Motion. So here's what I'll be covering in the video. I'll start with a brief introduction of the concepts involved in the lab, and then I'll discuss the experimental tracker data. After that, I'll go over my computational models and discuss comparisons, and I'll end by discussing further questions. So first of all, the purpose or the goal of this lab was to compare the projectile motion of an object in actuality, which I got from tracker data, versus a computational model, one with drag and one without. So to do this, I acquired data of an object exhibiting projectile motion and compared this data with a computational model that represents the predicted motion. So the actual real data was acquired by tossing a crumpled up ball, so it had projectile motion, and then measuring the x and y positions and getting their corresponding velocities. In order to set up an origin point, I used the calibration stick and made sure that my camera was fixed so I could get accurate data. Additionally, in this lab, the system is the ball and the surroundings are everything else, including air. So now let's review some key concepts and formulas that assist with the understanding of this lab. First, I'll review Newton's second law, which explains how the net force of an object is its change in momentum over its change in time. So from this formula, we can derive the velocity update formula and the position update formula, which relate velocity and position to force acting upon the object, respectively. It's also important to consider the forces involved in this lab. The gravitational force in this lab is near the surface of the Earth and is equal to the product of the acceleration due to gravity and the mass multiplied by negative, as this is in the negative y direction. G can be found by manipulating the law of universal gravitation, where we can rearrange to see that G equals 9.8 meters per second squared, regardless of where one stands on Earth. Another force to consider in this lab is drag force, which is caused by air particles in the Earth's atmosphere, as the medium in this lab is air. The drag force is opposite to gravity, and since in this lab gravity is defined to be downwards, drag would be upwards. Drag force is equal to the drag coefficient multiplied by the magnitude of squared velocity. Through this, we can see that the drag force will increase with time as magnitude of velocity of an object will increase, and this is due to the acceleration of gravity. So to acquire Fnet, we must add the gravitational force with the drag force. Now here's a video that shows the tracker data I acquired by tossing the paper ball into the air and recording its projectile motion. So the original position of the ball in this was 0.1760, and the initial velocity was 5.39, 3.850, which I acquired the velocity by subtracting initial versus final and then dividing by 2 from the first 2 frames. Now here's my GlowScript code I wrote for the computational models. First, in the top left, you can see my initial conditions such as velocity, position, and mass and time are present, and these were all acquired through the experiment just shown. And in the bottom, on the bottom left, you can see the loop, and in this, I calculated Fg and W separately in order to have drag and force due to gravity separate. So this means I only had to use one computational model, because basically, if B was equal to 0, W was also equal to 0, and drag would have no influence on the net force. Then you can also see in this part that my velocity update and position update formulas are present, the quotable equivalents, and these are used to track position and velocity for graphing. And lastly, on the right, you can see how my code is used to actually create the model of forces. So here are the results from my computational model. On the left, you can see the trajectory graph and the model when no drag is present, and on the right, you can see how a drag of 0.016 contributes to trajectory of the ball. Now here's a scatter plot that depicts the scaled version of the actual data I acquired through Tracker, the computational model with a drag of 0.016, and the computational model that has no drag. So this measures trajectory with the x and y axis is measured in meters. So in this graph, we can see how initially all observed and predicted values are similar. However, as the motion continues, the computational model without drag overestimates the change in position, while the computational model with drag underestimates the change in position. This suggests that there's a better p-value I could have used that would account for a more accurate value of drag force, since the observed motion lies in between the two. So some possible sources of error include incorrect placement of point mass in the tracker, and this would impact position. Another one is choosing the incorrect b-value that influences drag, and also having incorrect starting frame from the tracker may have been a source of error as well. So now let's discuss further questions. First of all, what does it mean? Do any of my models predict the terminal velocity? So yes, the model that incorporates the drag force does predict the terminal velocity, and that's the one located on the left with a more bent out shape and less linear shape. And in the computational model where drag force is involved, we can see that there was a decrease in the magnitude of the change of velocity. and this suggests that there is an asymptote present where the terminal velocity exists. What if? What if the object was thrown straight upwards? Well, this time that it would take to reach the ground would actually be longer, since there would be an upward acceleration when you throw the ball up, and gravity would be working against this. And this would just result in it taking longer time to reach the ball. Thank you.